Okay. This one, I think we set this up a little bit. At noon, Ship A. It's 100 kilometers west of Ship B. Let's see, Ship A is sailing south at 35 kilometers an hour. Ship B sailing north at 25 kilometers an hour. And then they asking me about noon to 4, so 4 hours later. 4 hours later, how fast is the distance between the ships changing? So this distance here. There you go. Later. All right. Makes sense. He's got a little further. Yeah. All right. So that's the setup. I think we set that up before. And then we were talking about maybe 2 triangles, and then we were talking about maybe one big ass triangle. So it's up to you the way you want to do it. So make one big old triangle. In general, so this I keep hammering this. This is where people make the simplest mistakes. There's a snapshot that they ask me about, but I have to draw the general representation of this situation, right? So what do I mean by that? They ask me 4 hours later, so I can figure out how far this ship has gone. But what do I call this distance? Really good choice would maybe be little a, the distance itself, and then I can say, well, what is this? DADT. I like it. And then, so incrementally enough, what am I going to call this distance? B is no way. And this is going to be DBDT. I like it. So let me ask you, if you make one big triangle out of this is where you got to be careful. This is related to somebody wondering about if something should be negative. So if I say that's 35 kilometers an hour, so this is A here, and it's moving at 35 kilometers that way. Then, what you can do is, this would be A plus B, right? But what can you call it if you want to? Maybe C. Sure, this is somehow makes sense. So if I say A plus B, see that this big, so let me draw this big old triangle I'm talking about now. So now I've got this big old triangle. This is 100. This is C. This is the distance I'm interested in. Let me call this S. Just because you already use C over there, right? Let me stop there for a second. Can somebody tell me what DC dt is?
60 kilometers.
Yeah, it's the sum of these. Right? Because after 1 hour, how far north is this gone? After 1 hour, 25 kilometers. After an hour, this has gone 35 kilometers. So that would be a total of 60. If I wait 1 more hour, this has gone another 25. This has gone another 35. So how much is it changing per hour? 60. So this is what I was saying when somebody asked me, do I want to make that negative because it's going down? No, these are 2 ships going away from each other. So in the context of how is this distance changing, it is increasing by the sum of both directions. All right, so that's, you could either do the 2 little triangles, or if you want to do the big triangle, you have to realize all this stuff. What's really nice about this is I consolidate all my DBT stuff into one statement. And what's the relationship between what I know stuff about and what I don't know? Yes, S squared. Yeah, exactly. And then you can take derivatives, and then you can plug in values. Is that cool? Basically, you're there. All right. All the work really should go into setting up the equation. The derivatives after this should be the easy step. So what would this look like?
2x ds dt.
And that's what they're asking me about, right? They want to know ds dt equals what? Equals gone, right? So the only thing I don't know is what C is, but I do know what C is. Right? Just let it go for 4 hours. 4 times 60. So then I know what C is. And then what's S? Yeah, I can use. See, that happens so often. The formula you just took a derivative of is the formula that's going to give you the variable that you don't know. Because that's the relationship that exists. Is that enough? I mean, I'm going to say that's enough because you're almost done. Right? I declare that enough. Yes?
For number 3, for E and F, I got up to what something was, but I don't know how you got the actual answer. Does that make sense?
Oh, E and F?
So I got 2 equals 0 and 16 over 3, but I don't know what you did after that.
Oh, I'm sorry. So it's 16 thirds hours, right? 16 divided by 3 is 5 1/3. What's a third of an hour? An hour is how many minutes?
16.
So what's a third of 60? 20. So it'd be 5 hours, 20 minutes. You don't have to go that far. You can just say 16 thirds hours. But if you actually said that to somebody, they're like, who the hell are you? You mean 5 hours and 20 minutes? Oh, yeah, I do. So I really want to say this again. When it's a word problem, don't, in general, if it's just a calculus problem, there's no word problem, there's no units, there's no nothing, it's just, take the derivative and plug a 5 in. Then you can give me the answer as natural log of square root of 7 over, whatever. But if it's like the distance of somebody's house or how quickly a volume is changing, don't tell me it's natural log of square root of 7 over 11. What the hell's that shit? You wouldn't say that to somebody. I said this before. If there's a word problem, write that so I can see you got the right exact answer, but then make it into something that a normal human would say, right? Math people, we do get a little wrapped up in math, but we are able to take it back down to 7.3 or something that actually makes sense.
For
Yeah.
the practice test, C, I understood most of the math. My question was the last simplification that you made when I was bouncing my answer off yours. I didn't know how you got that last simplification.
So I'm sorry, which C?
For 1C.
1C, okay. Oh, yeah. Oh, yeah.
The last simplification.
Let's see if I remember how to do that. So secant squared is, well, there's actually one more thing you can do there, but secant squared is 1 over cosine squared, right? And then tangent is sine over cosine. So you can, let's all double check my thing I did in my head here. Let's see. 3, so it's 3 times 1 over cosine squared over sine over cosine. Yeah. So I can do the reciprocal. So 1 cosine cancels. So let's see, what did I write down?
You wrote 3 sine.
Oh yeah, so I did that all wrong. So what should be 3? Are you guys cool with it? I mean, just multiply the reciprocal, of course, right?
Yeah.
And then in my brain, I think I turned something around here, but this should be 3 secant cosecant. Is that cool? Yeah. So thank you for that. That was one that I was like worried about, and then I forgot to go back and double check it. I'm like, oh shit, I don't know this right. What else you could do is what's secant squared? What's an identity with secant squared?
Get that formula. 1.
Yeah, what's equal to secant squared?
1
1 plus tan squared, right? And then you can break that up because the bottom's tangent, right? So that's another way you can kind of rewrite that. But normally if you have a ratio of trig functions, you try to see is there something that'll cancel, right? There's a simple thing I can do. And hopefully you do it right.
I was just wondering about the sine tan one.
I don't know. Let's see. Why did I do this? Sine? I'm trying to remember what I was thinking, but you never know. Cosine over sine. I don't know how I got the sine to survive and go up there. Oh well. Oh, you were also asking about part F, right?
Yeah,
So part F, if I figure out, and when I say get back to where it started started at where it was at time 0, right? So there's a little bit in there that you got to be careful about. At time 0, it was at the 0 position because S of 0 is 0. So then if I set S of 0, S of t equal to 0 and solve, I can see when it gets back to position 0. So there is like an absolute position. And that's what really this picture that they draw tries to capture. It starts at 0 because S of 0 is 0. And then it goes and then it comes back. And I want to know when else is it 0? When does it get back to that 0 position? So when I set S of t equal to 0 in factor, I get t is 0, I know that. That one I already knew. T equals 8, right? So after 8 hours, it's back to where it started. And so I know it takes 8 hours for it to get back to where it started. So I ask you, how fast is it going a half hour before it gets back? Well, a half hour before it gets back must have been 7.5 hours. And then I just plug that into the velocity. I like it. Yeah.
Oh, for that one, if it's negative, it just means it's going.
Yeah, so there we're considering, yeah, exactly. So we're sort of like set up to be that way's positive and that way's negative.
So we want the answer positive.
No, negative's good.
Okay.
Yeah, well, I said how fast is the train going, so if you put it in, I understand, because velocity can be positive and negative, speed can't. Yeah, so if you didn't put the negative, I'm totally cool with that,
Okay.
just because of the way it's worded. But if you put the negative, then you're looking at it like velocity, you're fine with that too.
Can you do these? Page 265. One of the four.
$87. Oh yeah. I put some other stuff on the bottom there. This just gets gross on the second derivative because you have multiple product rules, right? So you start with a product rule. So this 87 gives you, let's see. This is a position function. And very quickly, whenever you see this type, we know what that looks like. That's oscillatory motion, right? Anything in front of it would be the amplitude, and the amplitude is actually being adjusted over time by this guy. And as time gets bigger and bigger, this guy is getting, you can do it, it's e to the negative. So as time gets bigger, this term gets smaller. So this would be damped oscillation somehow. So if I had like a spring hanging off the ceiling and I pulled it down and I let it go, it oscillates like a cosine maybe, right? And over time it's going to slow down. The amplitude of those oscillations will decrease. So if you pluck a guitar string or if you pluck a spring hanging as you walk around, there's a spring, look at that. I say don't do that, it's probably better. Then it's going to have that kind of a term in it. In the function that describes its motion, it's going to have this kind of term in it. If it didn't, it would never dampen. It would be the absence of friction, which would be a weird place to live. You basically could never stop seeing however you started moving when you were born, that's it. That's where you're going. Sorry. So now I just got to take derivatives to find the velocity and the acceleration. Right, is that all we want? Yeah. Yeah. So do S prime. What's S prime going to involve, though? How many functions are there that's being a product of here? No. 2. There's 1. Because A is a constant. Any constant you can just slap together with a real function.
2.
All right, so with the variable in, there's 1, 2. So I have to do f prime g plus f g prime. My good old product rule. And then when you do the second derivative, you're gonna have to do that twice. Right? Does that make sense? Because you'll have 2 functions and each of them have 2 functions in them. Oh shit! Is that not good? How do you take the derivative of this? Yeah, it'll be a e negative ct times negative c. So when this exponent is a linear function, just the slope comes down. So the derivative of e to the ax is a e to the ax. And people sort of make the wrong assumptions. Well, then that means that the rule is bring that down. No, it's just because it's a very simple function in there. The derivative of ax is a. It still is chain rule. It's just you can just remember that's a shortcut for that. All right, and then what goes here?
Cosine.
Good. You can't take more than one derivative at a time, right? So that's this guy gets a turn, and then this guy's sitting there waiting, and then you leave this guy alone. And what's the derivative of cosine?
Minus sine.
Good. Negative sine.
Double.
And then of course
Inside.
the inside gets a turn. What's the derivative of the inside? Omega. W. We'll call it W. Let me stop there for a second. That's the first derivative. That's the product rule doing the first derivative. Second derivative, you basically have to do what we just did twice, because we have this term that looks a lot like this one does. So you have to do the same. It's going to get 2, just like this got 2. And then you have this one, it's going to get 2 answers for its own product rule. Camera's just barely hanging on. Yes?
What is that negative W there by the A?
Oh, okay. So remember, what's the derivative of cosine?
Right.
Negative sign. And then the derivative of the inside function is, I just put it out front because it's going to go there eventually. Is that all right? Like, what part of this problem gives the most trouble? I see a lot of troubled people out there. What part of this problem gives us the most trouble?
What's a constant? What's a number?
I got you.
That's a number.
The answer's right there. They tell you what it's a function of. This is a function of t. So every other damn thing you see in there has got to be a constant. I love that. Sometimes this book, I will agree, sometimes they don't tell you that. They say y equals ksat. What the hell? I totally understand that. But here, they did the right thing. If I said this, s of ct equals blah, 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 now both of these would be variables. Oh, shit. So that's what I mean when I said write it as a function of radius only. You're trying to get rid of all the extra variables, right? So then you can attack it directly. If I have all these variables, then it's got product rules and they have their own chain rules. Oh, shit. So thank God this is only one variable. Is that better? I mean, does that help? So that's the best way to write something, so you know exactly what the variable is, and everything else is a constant. Yeah?
101. I was just thinking, you wrote 400 and parentheses square root of 3. Does it anyhow work here?
Oh, I just did that just in case.
Just
Yeah, I don't know. I was just working it out. I'm like, oh yeah, what is x? And I'm like, oh, I don't need that. Okay, cool. Yeah.
okay.
So I don't know. I just put it there. Just, hey, look, this is true. Okay. But again, you know, so when you have Pythagorean theorem, let me see if you guys get this. Sometimes you have to go back and figure out the value of a when the height is 10 or something, because you're like the one we just did here. When you have this on there, I know I'm going to be left with an actual variable. So I got to know what the value of that variable is at this snapshot that I'm taking. So I have to go back and figure it out. If my function was s equals c plus 100, then I don't have to know squat. ds dt equals dc dt. Bam. Right? I don't have to know the value of s because it doesn't show up. So there I figured out what x was, and I'm like, oh, I don't need to know that. All right, no big deal.
Okay.
Yeah.
Sec is 3.10.
Oh, okay, okay. So number 33, 310 is that linear approximation, but they also has the differentials in there. 3.10, 33. The edge of a cube was found to be 30 centimeters. With a possible error of 0.1 centimeters. That's what delta x is. Use differentials to estimate the maximum possible error, relative error, percentage error. So that's just like example 4. It's exactly the same thing as example 4. They did a sphere measured with a possible error in measurement. Same kind of thing there, right? So the volume of the cube, what's the volume formula for this? Like it. So then, for example, what would dv dx be?
3x.
Or let's do it like this. What would dv be?
3x squared dx.
Like it. Right? You guys kind of with me? And then dx would be this, 0.1 centimeters, right? Because the idea is the change in x is going to be this. No matter if I look at it like this or like that, I can estimate using this full thing. dy or d whatever, that's going to be an estimate, right? Because this does not hold over that whole step I'm taking. It only holds for a nano step. This is a huge step compared to how far this really works, but this is why it's an estimate. So it's exactly like example 4. Right? So now I can just plug in 0.1 to there. X was 30, right? They didn't give me anything else. No, cool. I like it. Is that cool?
Yeah.
And the relative error makes it better. There's a problem in my stats class where they said American Airlines got 5,000 more complaints from customers than Air Tehran or whatever, right? Or some name of an airline I'd never heard of before. And they said, does this mean that American Airlines is worse? Well, it means they're bad, but does it mean they're worse? No, I got to look at the relative amount of complaints. I got to know how many freaking people did this little tiny company. If they got 30 complaints, but they only took 60 people somewhere, that's 50%. But 5,000 for American Airlines is like nothing. Right? It's a really good percentage. So it's all about, that's why you want to calculate the relative error. Because you can say, oh, we're off by 3 miles on our estimate. But we're talking about the 9th planet that has been discovered, poor Pluto. Some distance there. Something like, that's pretty good considering how freaking far away it is. That's good for resolution or something. Right? Not anymore nowadays, but oh well. Maybe me in the backyard. That's pretty good. That's good. Yes?
Which volumes are we supposed to memorize for tomorrow's test?
Alright. If I don't put a formula down, and you forgot what the formula is, just come up and ask me. If it's one more obscure thing, I'm going to put it down. Otherwise, I'm going to be hopeful. You should certainly know the volume of a cone by now. Really not? Really? Not? What do you cut a cone out of? You cut a cone out of a cylinder, and then I'm going, well, you should know the volume of a cylinder. You really should. And if you don't, it's the circle repeated this many times. So it's pi r squared h. You cut a cone out, 1/3 pi r squared h. And in general, now watch, real quick, watch. So if I had a square-based pyramid, it would have been cut out. This is kind of cool. I know, you guys are like, that's not a pyramid. If I cut out something that connected them all to a point, now for me, this is really damn good. Isn't that a pyramid sitting in there? Isn't that what that is? Thank you very much. So the cone is the most simple example. We would never call it this, but in math it is. It is the simplest pyramid. A pyramid is where all the edges come to a single point. Isn't that what a freaking cone does? So if I take all the vertices and take them to a single point, that is a pyramid. The volume of the cube, it's not a cube, but the volume of the solid is x squared h, right? So the volume of the pyramid would be 1/3 x squared h. That idea holds.
Is it the same with triangle prism? So
Sure, of course, yeah. So if I had a Toblerone, I want to draw one. It's hard for me to do that. It's hard for me to do any drawings, but you can actually make a pyramid out of this too. If you connected the sides to this, you could have a triangular shape that almost looks like what I want to, just leaning over. Oh well. So you can imagine the same thing. I don't know why I couldn't do this. Let me see. I should be able to do this. You could do this, Jeff. I don't have a clue. how to do this. Oh well, screw it. It's just gonna go straight up. How's it? That's horrible. So if I took all of these, that's still really bad. If I took all of these and I took it to a single point up there, it doesn't even matter where, to be honest. I could have put that point there, and it would have still been the same thing. That's horrific, but I'll get past it. So a triangular-based pyramid is just 1/3 of the volume of the prism. And what's the volume of a prism? It's freaking area of the base times the height. Area of the triangle times how long it is times 1/3 is a triangular-based pyramid. This is unfortunate that we don't know these things, because math, people think you got to memorize everything in math. No, I memorized like 2 things, and I know 28 things because I memorized those 2 things. Thank God, because I ain't got much space left. All right, but long story, very short. If it ain't on there, you don't know it, come up and ask. Kabam. Because most of the time you know it, you just don't feel confident to realize you know it. Yeah.
How do you graph 21 on 3.10?
Oh yeah, so figure 5. Where are you, figure 5? There's figure 5. Okay. Does this figure 5 itself make sense? That's where we have to start.
So you have the graph, the original function, and you have the tangent line.
Yes.
Yeah.
Yes, the tangent line. So dy is how far you go to the tangent line. Delta y is the actual distance to the function. So what function do they give us? 21, 2 over x. So what does that look like around 4? 2 over x. What does that look like? So if y equals 2 over x, what's happening at 0?
Zero to nothing.
Asymptote. There's so much is happening. No, the opposite of nothing. Everything's happening. It's going to infinity. At 1, what is it? 2. All right. At 2, what is it?
1.
That's crazy. At 4, what is it?
1/2.
1/2. All right. So we should all know this shape, right? It's the simplest hyperbola there is, because it would have another shape over here, and I don't care about that side, because I'm talking about that side. So all the action's happening right here, because it says that x equals 4, right? Where'd it go? 21, x equals 4, delta x equals 1. So just like in figure, what was it?
5.
Figure 5, you start at the point you're interested in, and you go up. So how much would I go up by? How much would I go over by? Let me say it like that. How much does x change? 1, yeah, okay then. So I would just take this and zoom in. So I wouldn't draw this because it's got a lot of stuff I don't care about. Right? I would just zoom in on that. So I'd say, all right, here I am at 4. In fact, don't get out of there. Here I am at 4. Just put there for reference. So then at 4, so I would say this is 1/2, 1, 1.5, so forth. So that's 0.5, 1, 1.5. So at 4 is 0.5, right? And so it's coming in like, I guess we should do one more thing. 3 it would be 2/3, 0.6, so it's like right there. We need an even better scale. I think you see what I'm saying. So an even better scale I can make. I can zoom in even more. I can zoom in and say, okay, let this be 0.5. All right, and then this is 1. So here's what's happening at 5. Oh, this Jeff dies. It's been a good life. 2/5, which is also known as 0.4. All right, so 0.4, maybe about right there. So everything's happening there. So this would be my delta x here, right? Is 1. So what's dy? So where's my tangent line? It's going to come in like that, roughly. So I really want to see. the whole difference between delta y and dy, I might even want to blow this up a little more because it's all happening right there. See the difference there between where the function actually is and where the tangent line is after that delta x? That's where everything is happening. So dy, and here's delta y, because that's how far down it goes to get back to the point on the graph, right? And then dy, at 5, it looks like the tangent line's there, so dy would be a little bit further. So that would be dy. Again, because what is delta y? Delta y is, dy is the tangent line. It's what the tangent line is doing. Delta y is what the function actually does. It's the real change in y. Dy is the estimate using the slope at a point that's way back here. That's why when I get 1 point over, it's going to be off by a bit. It's not off by much, so you might even want to zoom in more. All right?
So at the, between 4 and 5,
Well, delta x is 1. So when I do take that step, dy is a little further down than delta y is. Delta y just goes to here. Dy has got to go down to there. So this is delta y. This is dy. All right. Again, it's all about zooming in so you can see what's going on. Because it's not, they didn't pick the greatest function. It's not much going on at 4. They should have made it back here. It would have been easier. Look at that difference. Holy shit. That would have been a little easier in here, but oh well.